The graph shows us the fuel consumption in litres per 100 kilometres, depending on the load carried. Now you can see here, we've got quite a few data points. It's a very strong positive correlation off the top of the appearance of the graph, and the actual point there, 12.3 is the real figure, prediction below. The equation F is equal to 1.6 W point plus 8.4. Now when we show the residual, this is a departure of the given points from the modelled linear equation. So in other words, when we're looking at a 2-tonne truck, it's only 0.7 above the prediction for the line. Now the features we look for a residuals graph for when it's well modelled are the following. We've got a reasonable number of points, they're randomly distributed above and below the line. There is no distinct pattern. A pattern can lead us to suggest another model, which we don't look at in this course. Perhaps a nonlinear model may well be more applicable. So I could write random distribution of points above and below the axis. There's no discernible pattern. Although not part of this course, some students have told me with this question that the magnitude of the residuals are quite small as well. Now looking at the highlighted point of A2, 12.3, that tells us that a truck with 2 tonnes of load consumes or uses 12.3 litres per 100 kilometre. Now that's slightly above the zero residual line or the modelled equation line. Now if we plug that into the equation, we'll actually end up with a prediction of 11.6 litres per 100 kilometres. Now the residual value for this point, we don't look at this too often, is simply the subtraction between the actual, which is 12.3, take away the 11.6 or 0.7 litres per 100 kilometres. So the actual fuel consumption for a 2-tonne truck is 0.7 litres per 100 kilometres, more than that predicted by the equation.